Hello, Accelerated Chemistry students. This is Miss Crisafoli, and this is your Chapter 13, Section 2 video notes all over the nature of liquids. So let's talk about models of liquids. So substances that can flow are referred to as fluids. Both liquids and gases can flow. So the ability of gases and liquids to flow allows them to conform to the shape of their containers. So as we look in the pictures down at the bottom, we can see that solids can maintain their shape, where liquids and gases fit their containers. Liquids will take the shape of their container as well as gases, and gases completely expand to fill their container. So gases and liquids have a key difference between them. According to kinetic theory, there are no attractions between the particles in a gas. And that makes sense because the gas particles are so far apart from each other. Particles in a liquid, on the other hand, are much closer together, so they are attracted to each other. So these intermolecular attractions, remember, we talked about these in our Chapter 8 over bonding, which talked about dipole-dipole, London dispersion. We also talked about ion dipole and then hydrogen bonding. Those are all your intermolecular attractions. Those are the attractions that happen between the molecules. They keep the particles in a liquid close together, and that is why liquids have a definite volume. So the interplay between the disruptive motions of particles in a liquid and the attractions among the particles determine the physical properties of liquids. Liquids are much more dense than gases. When increasing the pressure on a liquid, it has hardly any effect on the volume. And this is the same for solids. Liquids and solids are known as condensed states of matter. So the conversion of a liquid to a gas or vapor is called vaporization. When this conversion occurs at the surface of a liquid that is not boiling, the process is called evaporation. So when something is boiling, the bubbles are coming from within the actual liquid. When something is evaporating, the bubbles come from just the top of the liquid. They're not coming from deep down within the beaker or the graduated cylinder where you're boiling your liquid at. So the process of evaporation has a different outcome in an open system, such as a lake or an open container, than a closed system, such as a sealed container. So in an open system, molecules that evaporate can escape from the system. In a closed system, molecules that evaporate or vaporize will be collected, and they will condense and then go back into the liquid. So during evaporation, only those molecules with a certain minimum kinetic energy can escape from the surface of the liquid. Even some particles that do escape collide with molecules in the air and rebound back into the liquid. So a liquid evaporates faster when it's heated, and that is because when we heat a liquid, we are increasing the average kinetic energy of the particles. And the added energy enables more particles to overcome the attractive forces keeping them in the liquid state. So as evaporation occurs, the particles with the highest kinetic energy tend to escape first. The particles left in the liquid have a lower average kinetic energy than the particles that have escaped. As evaporation takes place, the liquid's temperature decreases. Evaporation is a cooling process. We talked about this yesterday when we talked about our drinking bird demo. So when evaporation happens, when the water vapor on your skin or the water as a liquid on your skin, when you get out of a pool, when that starts to evaporate, you feel cold, and that's why you grab for that towel over the summer. Not because it's colder outside than it was in the water. I want you to think about that. You can observe the effects of evaporative cooling on hot days. When you perspire, water molecules in your perspiration absorb heat from your body and evaporate from the skin's surface. This evaporation leaves the remaining perspiration cooler. So the perspiration that remains cools you further by absorbing more body heat. So now let's talk about vapor pressure. The evaporation of a liquid in a closed system differs from the evaporation in an open system. When a partially filled container of liquid is sealed, some of the particles at the surface of the liquid will vaporize. These particles collide with the walls of the sealed container, producing pressure. A measure of the force exerted by a gas above a liquid is called its vapor pressure. Over time, the number of particles entering the vapor increases, and some of the particles condense and return into the liquid state. This happens in what we call an equilibrium. So we have liquid going to a gas, and we have gas going back to a liquid. So eventually, the number of particles condensing will equal the number of particles vaporizing. In a system at constant vapor pressure, a dynamic equilibrium exists between the vapor and the liquid. This means the rate of evaporation of the liquid is going to be equal to the rate of the condensation of the vapor. At equilibrium, the particles in the system continue to evaporate and condense, but no net change occurs in the number of particles in the liquid or vapor. When we were talking about vapor pressure and temperature change, I want you to think about a couple of things. We talked about this yesterday. An increase in the temperature of a contained liquid increases the vapor pressure. We talked about this. If you increase your pressure, you're making your molecules move faster. Your temperature is normally how you're going to do that. So when we're talking about it when vapor pressure, when we increase the temperature of the liquid, we're going to warm the liquid, and the liquid is going to increase in kinetic energy. So the more of the particles will reach the minimum kinetic energy necessary to escape the surface of the liquid. So how do we measure vapor pressure? Well, vapor pressure of a liquid can be determined by the device called a manometer. So this is what it looks like. So basically you have a flask, and then in that U-tube, you're going to have some mercury. Now, this is an old school technique. So the vapor pressure is going to be equal to the difference between the two heights of the mercury. So if we have more vapor pressure, then that difference is going to be larger. Now let's talk about boiling point. When a liquid is heated to a temperature at which particles throughout the liquid have enough kinetic energy to vaporize, the liquid begins to boil. Bubbles of vapor form through the liquid, rise to the surface, and escape into the air. The boiling point is the temperature at which the vapor pressure of the liquid is just equal to the external pressure on the liquid. So when we change pressure, we will change the boiling point. So because liquids boil when its vapor pressure is equal to the external pressure, liquids don't always boil at the same temperature. Because atmospheric pressure is lower at higher altitudes, the boiling point is going to decrease at higher altitudes. So let's look at this. We're looking at the sea level and then Mount Everest, and we're looking at where water is going to boil. If we are at sea level, we're going to start at 70 degrees temperature water, and it will not boil because we are not at the correct boiling temperature. We're at 70 degrees and not 100. When I heat it up to 100 though, we're going to get water to boil because that's the temperature in Celsius that water boils at. Now, what if I go on top of Mount Everest? Well, that's a very high altitude, so the boiling point is going to decrease. So boiling is a cooling process similar to evaporation. So the vapor produced is at the same temperature as that of the boiling liquid. Although the vapor has the same average kinetic energy as the liquid, its potential or stored energy is much higher. So thus, a burn from steam is more severe than one from the equal mass of boiling water, even though they're both at the same temperature. Remember, those gas particles are going to be at a higher energy. So let's talk about normal boiling points. Normal boiling point is defined as the boiling point of a liquid at standard pressure, which is 101.3 kPa or 1 atm. And here are some boiling points for several things that we know. And as always, all of the information on these Google Slides has been acquired and adapted from Pearson Chemistry's 2012 edition of the textbooks, resources, CD, and pearsonchem.com. Thank you so much. Have a good night.